Hi, so here we want to look at the phase portrait for this system right here. And why can we do a phase portrait? Oh, because it's first order, so this is a slope. So we can visualize it as a bunch of little slopes. And it's telling us to use a computer software to attain the phase portrait of the system in problem 5. If possible, include the arrowheads and also include 4 half lines in your phase portrait. So I went ahead and graphed it in advance. Here, let me pull it in for you. And I'm gonna move it. How about we move it here? There it is. So I graphed it. And what do we notice? Well, we notice this eigenvector and this eigenvector. And these are the famous spans that I'm saying, hey, if the eigenvector is this long, it doesn't matter because it'll still stay on this line. And this is really the information that we are looking for when we're solving these homogeneous first-order linear systems. So all of this, let me erase this. We did part A. Let's look at part B. Obtain the Cartesian equation for each of the 4 half lines in the plane. So looking at my eigenvalues and my eigenvectors, I know that my general solution, x, is going to be equal to c sub 1 times my first eigenvector, which is -2 minus 8, all multiplied by e to the first eigenvalue times t, plus c2 times my second eigenvector, which is 20 and 8. I can see it from the plotter, multiplied by e to the 8t. Okay, so now I can rewrite this in algebraic form as x is equal to c1. Well, if I assume that this is my vector x and y, then I can say that this is my x is equal to -2c1 e to the -10t plus 20c2 e to the 8t, and y is equal to -8c1 e to the -10t plus 8c2 e to the 8t. And once we have this, we can say, okay, if I'm looking at the first one, or if I'm looking at these two, I'm saying let t go to infinity. Now, if t goes to infinity, you should see that the terms that are to the negative power will be very, very small because, look, if I have e to the -1, this is 1 over e. If I have e to the -2, this is 1 over e squared. If I have e to the, let's say, -10, this is going to be 1 over e to the 10. So this number in the denominator is going to get larger and larger. And as you divide 1 by a larger and larger number, you're going to get closer and closer to 0. But infinity is so large of a number. It's not a number, but it's so large, it's so far that we can say that those terms are 0. So we can say that x is equal to 20 c2 e to the 8t, and y is equal to 8c2 e to the 8t. So we have this term in common. So why don't we solve for this and eliminate that? Well, then we get x over 20 is equal to c2 e to the 8t, and y over 8 is equal to c2 e to the 8t. Now we can write x over 20 is equal to y over 8, or y is equal to 8 over 20 times x, which is equal to 4 over, sorry, we can divide by 2, so divide by 4, so we get 2 in the numerator and 5 in the denominator, x. And this should be as I go to infinity. So as I go away from the origin. As I go away from the origin, you notice these arrows are pointing away, these are pointing towards the origin. So those are going to be for my negative. So those are going to happen. Let's see, when could those happen? I think when we let t go to negative infinity. Do you see why? Well, if I let t go to negative infinity, these terms over here will be multiplied by a negative number that's always larger and larger and larger, and eventually the negative and the negative cancel out and we get a positive. So they're going to get very, very large. So they're going to go very, very large, and these are going to get smaller and smaller because they're going to be to a power that is negative and getting larger and larger. So we can say that those last two terms, go to 0, and we can rewrite the expression, the system, as negative 2c1 e to the negative 10 times t, and y as negative 8c1 e to the negative 10 times t. Now we see, oh, sorry, I didn't want to show you another problem. We see here that this is in common. So why don't we eliminate that by dividing the top one by negative 2. So I get x over 2. Negative x over 2 is equal to c1 e to the negative 10t. And here I get negative y over 8, if I divide by negative 8, equal to c1 e to the negative 10t, which allows us to say that, hey, if x is equal to this and y is also equal to this, then this must be equal to this. See what I'm saying? So we'd have negative x over 2 is equal to negative y over 8. The negatives cancel out, and then we can multiply both sides by 8, and we get y is equal to 8 over 2x, which is equal to 4x. So the other one here is 4x, and it's going to point in because the original exponent was to the negative power. And that was part B. Draw the eigenvectors on your face portrait of the system. We have them. They're these black things. This looks like is the vector negative 2, negative 8, scaled down a little bit if you look at the scale here. And this looks like the vector 28 scaled down again, but you see that the x is way longer than the y, so it kind of makes sense. All right, I hope this was useful, and I'll see you next time.